All right, guys, this is the last thing we're going to learn about probability. It looks like I'm going to push your test to Wednesday instead of Tuesday. And I won't be here on Wednesday, but you'll have no problems working it out. So today we're going to talk about independent events. So last class we talked about conditional probability, and that means that if you're given some event, what's the probability that a second event will happen? Well, in this case, these are two events that have absolutely no relation to each other. So one does not affect the other. So for example, if you flip a coin, the probability of getting heads is 1/2. If you flip a second coin, just because you flipped heads on the first day or on the first flip, doesn't mean that it's going to impact your second flip. You still have a probability of 1 out of 2, as long as it's a fair dice. And so what you can say is that if you're given event A, for example, flipped a coin, got heads, and you flip a coin again, that would be event B, the probability is still just going to be whatever the probability of B is, and vice versa. So here's a little here's a paragraph you can read. Two events are independent if knowing one event occurred doesn't change the probability of the other event. So for example, if you're flipping a coin and it shows heads, but then I told you, okay, it's Tuesday, flip your coin today, it's not going to matter, because it doesn't matter if it's Monday or Tuesday, or Wednesday for that matter. If you flip a coin, you're always going to get a 50-50 chance. But not every situation is that obvious. So like, if you're talking about gender and left-handed versus right-handed, so 10% of the entire population are left-handed, but 12% of males are left-handed. So these events actually are not independent, because if you know a person is male, their probability of being left-handed is actually going to be increased, because 12% of males are left-handed. So there's more left-handed males than females, which is interesting. So again, you know two events are independent if you calculate their conditional probability and their just regular probability, and those two things are even. And let's remember that conditional probability, so the probability of A given B, is equal to the intersection of the two divided by the given. In this case, the given is the probability of B. All right, so let's look at some examples. This first example is income and universities. And so we've looked at 2 universities, and we've looked at 300 graduates who responded to the survey, so they were voluntary responders. And they talk about their annual incomes. So we want to know, are the events 40,000 and over, and attending University B independent? So the first thing we have to do is calculate the first event, which is here. So we'll call this P of A. So 40,000 and over, we can see that 40 out of the 300, I'm sorry, 75, my bad. 75 out of the 300 people have indicated that they are in this category. And if you look at the combined category, that is the 2 together, you'll notice that it's 40 over 120. So this is the probability of A, and this is the probability of A and B together is 40. And then you're going to put it over the total here. That's your given information. All right, then if you divide this out, so the probability of this is 0.25, and 40 divided by 120 is 0.33. And since 0.25 does not equal 0.33, no, these are not independent. Now, if the numbers are close, like 0.25 and 0.26, yeah, they're independent. But these are not close enough to say they're independent. Let's look at another example where they are independent. So, again, we're looking at the same set of data, But this time we're going to look at income under 20,000 and University B. So the first thing we have to do is find the probability of event A, which is an income under 20,000. So if I look here at this column, I see that it's 60. And it's going to be 60 out of 300, because that's my total. And if I'm looking at this combined, so this would be the P of A intersecting with B, I notice that that is, A and B together is 24. Right here. Over the total, which is the given information of University B, which is 120. When I divide these out, I get a probability of 0.2 in both cases. So yes, these two events are independent. Because 0.2 does in fact equal 0.2. So one event doesn't impact the other. So it doesn't matter if you know your income is under 20,000, whether or not you have a salary of under 20,000. All right, let's look at Finger Lake. All right, so in this problem, we are looking at if there's a relationship between females and finger length. So in this table, you'll notice that we're comparing the two things. And one thing you have to note is that there are a total of 452 students that were surveyed. So the first thing we want to know is, what is the probability of female? And you'll notice that there are 212 total females. Right here. So we want to do 212 over 452. So when you divide that out, 212 divided by 452, you get 47.47. So that's our probability of being female. Now we want to know the probability of being female with a longer ring finger. And so that's intersection is right here. So the probability of female given ring finger is longer, while the probability of both is 82, and then the given is the total ring finger people, which is 234. So if you divide 82 by 234, you end up with 0.35, and since 0.35 does not equal 0.47, these are not independent events. That means that one, knowing the gender, has an impact on which finger is going to be the longest. Bet you didn't know that. All right, here we go. We've got looking at males and seeing if this is the left-handed, right-handed situation where we said that there were more males that actually have, that are left-handed than females. And so let's look at how we can see that these events are not independent or are independent. We'll see. All right, so the probability of male and then the probability of left-handedness, we'll say is event B. So the first thing we have to do is find the probability of being male. So your male total is here. So it's 23 out of 50 people that were surveyed. And 23 divided by 50 is 0.46. Then you want the probability of both situations happening. So the probability of A given B, and the intersection of the two is we're looking at left-handed, which is 3, left-handed and male, sorry, which is 3, and then the given event is the total lefties, which is here, and that's 0.43. Now, 0.46 is not congruent to 0.43, but they are close. So this would be a place where there's an argument, depending on how well you defend your case. But because they're not within 100, I would say they're not independent. And also because our survey size was small, I'm going to say they're not independent. But I'm saying maybe if the survey size were larger, might have a bigger impact. All right, so the general multiplication rule, we learned this one. If you're looking for any two events, so that means they can be dependent events. For example, event A does impact event B. This is the multiplication rule. If you want to find that intersection where the two cross, and it's not already given to you, A intersecting B, you could take the probability of the first event times the probability of the second event given the first event. So remember, this is the formula for finding the probability of B given A. Or you could do it vice versa. The probability of B, so the probability of event B times the probability of event A given B will also give you this event. Now, if you know they're independent events, you could just take the two probabilities and multiply them together because there's no overlap. All right, let's look at drawing cards is a dependent event because if you draw a card and then you draw a second card, you have less cards the second draw because you've taken one out. So let's say, for example, we want to know the probability of getting a black card after you select a black card. So your first situation is you're going to select, I'm sorry, you can't read this, a black card or a red card. And as we know, there's a 50-50 chance because half the cards are black, half the cards are red. There's 26 out of 52 black cards. But now you've selected a card. So now you're not looking out of 52 anymore. Your next card could either be black or red, but this isn't, so this is 26 out of 52, but now you've taken a card out. So now your opportunity is, say you've selected a black card, so selecting black again would be 25 out of 51, but selecting red would be 26 out of 51, because you still have all the red cards in the deck. So the probability of getting black and then black again would be 26 out of 52 times 25 out of 51. And you just multiply straight across. If you were flipping coins twice, so let's say you wanted the probability of getting heads and then heads again, right? So you've got a 50-50 chance of 1 out of 2 to get heads and a 1 out of 2 to get tails. Now, if you flip heads the first time, you can now get heads or tails. And again, you have a 1 out of 2 chance. It didn't change. And so the probability of getting heads and then heads again is 1/2 times 1/2, which is 1/4. 1 out of 4 outcomes will be heads and then heads. Okay, go ahead and try the next 2 examples. Well, let's do this one together. So in this situation, we're looking at a jet taking off, and it says that the probability to succeed is 0.97, and there's going to be a total of 6 attempts. So literally, you just multiply 0.977 times itself 6 times. Or the shortcut for writing this is 0.977 to the 6th power. And that will give you your answer of blah, 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 0.8696. Because it's independent, you just multiply it by itself. This example, go ahead and try it on your own. Okay, this last example is one other one where you just have to know, if you see the word at least one woman, the first thing you have to do is find the complement of whatever's given. So this is saying that 5% of normal pregnancies receive a positive test. You want to know if 100 women go in, who's going to receive a positive test. So the first thing is you calculate the complement of the event that's given. And then we know that's 0.95. And there's 100 women. 100 women are surveyed, so you're going to raise it to 100 because each person is equally likely to have a positive result. And you get this answer. And then you got to go back, so that's the complement of what we're looking for. So then you go back and subtract that from 1. So